Welcome to Sigma Solver guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. Today we are going to see a new topic which is logistic growth model. So let's read the question first. The logistic growth model describes the population growth of a species with limited resources, which is important here, and is given by the equation dp by dt equals r times p into 1 minus p by k, where p of t is the population at time t, r is the intrinsic growth rate, k is the carrying capacity of the environment. Tasks which we are given for this question are: theoretical first, derive the solution of the logistic growth equation for the initial population P0 equals P0. Next, discuss the behavior of the population as t tends to infinity. And then we have a practical solving problem, which is implement a numerical solution using a programming language or software, example Python, which we are going to use to simulate the population growth for the following parameters. We are given r equals 0.5, k is 1000, initial population P0 is 50, and we need to simulate from t equals 0 to 50. We need to plot the population P of t versus time and discuss how the population approaches the carrying capacity over time, right? So that was the question. Now let's figure out the objective. So the objective is to model how the population grows in an environment with limited resources, right? So the difference between other model which we are going to see lies in this particular phrase. Next, the logistic growth model is a mathematical model used to describe how a population grows rapidly at first and then slows down as it approaches a maximum sustainable size called carrying capacity, right? So this defines what is a carrying capacity. Next, we are given dp by dt equals rp times 1 minus p by k, where p of t equals the population at time t, right, normal. Next, r is the intrinsic or natural growth rate of the population, k is the carrying capacity, right. Then we come to see what is the difference of this particular model, which is logistic growth model, from the exponential growth model, right. We have been using a exponential growth model for radioactive decay and stuff like that. Let's see how it is different from logistic growth model. So exponential growth dp by dt, where equals r into p, assumes infinite resources, right, which is unrealistic in real world setting. Instead, logistic growth model starts with exponential growth, which we will see, slows down as resource becomes scarce, which is very natural, right. Next, levels off at k, where environment can no longer support more growth. So when the resources get exhausted, so then we come down to the carrying capacity level k, where the environment can no longer support additional growth from here. Now we will derive the solution for this problem. Separate the variables first. So 1 by p times 1 minus p by k times dp equals r into dt, right. We are now separating dp and dt, right. We will use partial fractions on the left first. So 1 by p times 1 minus p by k can be written as 1 by p plus 1 by k minus p times 1 by k. So then we will integrate this up. Integrating separately, we will get integral of 1 by p plus 1 by k minus p times 1 by k of dp, and then which is equal to integral of r dt. We will use a common trick for logistic expressions, which is this one, where integral of 1 by p times 1 minus p by k into dp equals integral of k by p times k minus p dp. You can do this by simple maths as well, right. Now we will use partial fractions, where k by p times k minus p equals a by p plus b by p, where a and b are arbitrary constants. We will solve this for a and b first. So k equals a times k minus p plus bp, and k can be simplified further. right? So we'll match the coefficients from above. K equals A into K, so A equals 1, and P equals 0 times B minus A, so B equals 1 as well. Then we integrate using these two values. So integral of 1 by P, so we replace A by 1 plus 1 by K minus P, right? So if we go above, we see there is B here, right? So we mark B as 1 and then integrate it with respect to dp. So integral of r dt on the other hand, we will get ln log base e of absolute value p by k minus p equals rt plus c, where c is the constant. Then we solve for pt again. So for that, p by k minus p equals c times the same c as above, e raised to power rt, where p equals this expression, right? We use the initial condition where p0 equals p0 to find c now. Okay, so we'll simply put t equal to 0 and then find c, which comes out to be p0 by k minus p0. Then we'll have the final solution, which is replacing c back into the equation here. So p of t equals 1 by 1 plus k minus p0 by p0 e raised to power minus rt. Then we'll analyze the behavior as t tends to infinity, right? So as t tends to infinity, e raised to power minus rt will tend to 0. So p of t equals k by 1 plus 0, which comes out to be k. Now we'll have to interpret this, what this actually means. The population stabilizes at carrying capacity k. That is the actual meaning of this particular statement. So the practical implementation of this one is numerical simulation using Python. So for that, we are given r equals 0.5, k equals 1000 and p naught equals 50, right? So you can pause the video here and basically try out a numerical solution yourself, right? Okay, so once you have made that Python code for yourself, now you can verify it by the code below. So first we import numpy and matplotlib. Okay, we define all the parameters here, right? As you can see, t max is 50 and dt is 0.1, which is the time step, right? So then we arrange t from 0 to t max plus dt, and the step size is dt again, right? And right, so we got a particular array here. Now p will be the array of same size as t, but it will be filled with zeros. Okay, so p0 is p0, right? We'll have to modify this because it was given in the question, and then we apply the Euler method. So for I in range 1 to len t, dp dt equals r times of p I minus 1 times 1 minus p of I minus 1 by k, right? And there we again define pi, which is pi minus 1 plus dp dt into dt. Okay, so dp dt here stands for dp by dt. Okay, so now we'll have to plot this. So we'll have the figure size and plot accordingly, right? So we are using green color for that, and everything is same. It's just we'll use the PRT grid true and then PLT show to actually show the graph. Okay, so for that, first the two important statements is PLT plot, which gets t as the first parameter downward, and then p, which is the population, right? And then PLT show will actually display it. So for the output, you can use the below description to basically verify your plot as well. So in the output, you should see the initial growth exponential, right? Fast growth when population is small, right? So resources are high and the population needs are very less. So that goes for exponential growth. Then the next half of the graph would be slowing down as p approaches k, which is another threshold of population. The growth will be seen to slow down. And lastly, the stability. Eventually, when the population settles at carrying capacity k equals 1000, then we will see a straight line in terms of population versus time, right? So that is how you can use the Euler method in defining logistic growth model and helping you plot it using Python, right? So that's been it. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.